Hello, Calculus 1. We're still in section 3.2. I got a couple more ideas here at the end of section 3.2 about rates of change. These are kind of application problems. In real life, population might change over time. Water can flow and change. The water flow can change over time. And anyway, you can move over a distance over a period of time. And so that's one of the applications I want to discuss here. So we use S of t to be a position function as a function of time. So we mean the position of something that's moving. So it's position. Another word for that is distance. Or if it's falling, maybe we call that the height. The distance is the height. But in general, we use the word position. So we say position as a function of time. We use the letter S. S is a function of t. So anyway, that could be distance or height. So if I do the change in the distance over the change in the time, maybe you know that as a rate. The change in distance over change in time is a rate. It's the speed. We might know it as velocity. So the change in the position over the change in time is an average velocity. That's good old pre-calculus. That's actually the change between 2 points, 2 distances, 2 times. Change in distance, change in time is an average velocity. But when you take the limit as delta t approaches 0 of the change in position over the change in time, then that's a derivative, and that's ds dt. And it's the rate of change of the position with respect to time. It's s prime of t, and it's still a velocity, but now it's an instantaneous velocity. It's the velocity at one particular moment. So, and we learned, it's analogous to, if it was just a math problem with no units, no distance, no time, we call it the slope of a tangent line. But when that y becomes distance and x becomes time, then it's ds dt, and it's s prime of t, and it's velocity at any particular moment, instantaneous velocity. So that's a big physics concept, and just to add to that real quick, if the velocity is changing, and the rate at which the velocity is changing is the derivative of velocity. And maybe I haven't talked about this yet, but you can do derivatives of derivatives. Those are called higher derivatives, second derivatives, third derivatives. So that's coming up in a couple sections, but it's worth mentioning now. The derivative of a derivative is called the second derivative. And when it's the velocity that's changing, that means the velocity is changing. That means you're speeding up or you're slowing down. And the word for that is acceleration or deceleration, or we call it acceleration. And so that's what I want to say, just to finish this thought, that if I took the derivative of this derivative, the notation is s double prime of t. That's the second derivative of him. It's the first derivative of him, and that is acceleration. So that's 3 big physics ideas there, or application ideas. That s of t is a position function, and its derivative, s prime of t, is velocity, and its derivative, or the second derivative of position, is acceleration. So cool. We won't use it, well, yeah. All right, so I want to do a real problem, but let's get it set up here. So we are going to talk mostly about falling objects, and so then our height is going to be our position. But we'll just use position, s of t. And when something is falling, it's under the influence of gravity. That's what causes it to fall, and gravity is the acceleration, to tell you the truth. But anyway, the formula is this. The position function, s of t, is negative 1/2 g t squared. T is time. S of t is the height, or the position, and g is gravity, plus v with a subscript 0 times t. We call that v naught, v aught, v sub 0, little subscript 0. That's a number in front of t, plus s subscript 0, or s naught, or s subscript 0. So this is the height. This is the formula for what we call a free falling object. It's in free fall, free falling object. And one of the things we're doing in this formula is we are ignoring air resistance. So if we took into account air resistance, that would get a little more complicated. We'll do that in some higher calculus, but not for now. We ignore air resistance. I'm going to write that here. We're ignoring air resistance. So we do have gravity in this formula, and we're on Earth most of the time, but we could do another problem with some other planet or some other gravity. But on Earth, gravity is this number, mostly averages about this number, 32 feet per second per second. 32 feet per second per second. Gravity is, it is an acceleration. It's the acceleration due to gravity. And it's speeding me up as I fall toward Earth. It's speeding me up at a rate of 32 feet per second every second. That's if our distance is measured in feet. We also have another number for gravity. We also use 9.8 meters per second squared. And I'm going to put per second squared. It's per second, but I could write per second squared is another way to say that. Okay, and then this V naught was the initial velocity. I'll write that right here. Initial velocity. Now, don't confuse that word. Initial velocity. That's the velocity when I throw an object up in the air or drop an object or throw it down. I'm releasing it with some initial velocity. So it's the velocity at time zero. That's the subscript 0. We call it the initial velocity. Don't confuse that word with instantaneous velocity. This is the velocity at any moment during its trip. The initial velocity is just initially, of course. And that S naught is the initial position, or the initial height in this case, or initial position. All right, well, good. I'm going to use that formula, and we're going to do a problem here. So here's a problem. I wrote, here it is, it starts over here. It says, I threw a baseball straight up in the air with an initial velocity of 56 feet per second. All right, let's just stop that a second. I threw it up with an initial velocity of 56 feet per second. So this number is my V naught. So I can put that in the formula. From the top of a building that was 88 feet above the ground. Okay, well, I think that was my initial position. I think that was my S naught, or S sub 0. So that's what these two numbers are. And because I'm dealing with feet, then I'm going to use this gravity of 32 feet per second per second. Gravity pulls us in a downward direction. It is negative, but I didn't put a negative sign here because I got the negative sign in the formula there. Negative 1/2 times the gravity. I got the negative sign there. But here we go. The first question is, find the position equation. So the position equation is right there. And the position equation is the position function S of t, and it is negative 1/2 times the 32. This is classic, negative 16t squared, plus the V naught times t. The V naught is that 56 times t, and then plus the initial height, 88. So that was easy. I just needed that formula. That's the position equation. By the way, it helps to draw a little picture of this. I'm going to get a little picture right here just to get you thinking. The x-axis is t, actually. We're doing this as a function of time. So this is time. And then the y-axis is the height, s of t, or position, s of t. And I started at a position of 88. At a height of 88 is where this problem starts. And or I could do this when t is 0, I get a height of 88, but I knew that. And then, you know, it's just an upside down parabola. It's an upside down parabola. So you throw this, I threw this baseball up in the air. Of course, it's going to slow down, actually, as it goes up. It's going to actually reach a maximum height, and then it's going to start falling toward Earth. It's going to speed up as it goes. So there's a rough picture of it. All right, next question. Next question wants the velocity equation. The velocity equation is the derivative. The derivative of position is velocity. So here it is. It's an easy derivative, you guys. It's called S prime of t, although I might want to call it V of t also. It's its own velocity equation. And it is the derivative using a little power rule. It's so easy. Negative 32t. That's how you use the power rule. Plus 56. That's how you use the power rule, right, you guys? The 88 goes to 0, and there it is. This is my velocity equation. This will tell me, this is the derivative, and it'll tell me the velocity at any particular time. If I have a time, I'll plug it in. All right, so that's pretty easy. Get us going. And now I want to ask a bunch of questions about that. I have one question, C, here, and then I've got D, E, F, and G all right over here, and we'll work through this problem. The first question here is, when does it hit the ground? When does it hit the ground? That's not even really a calculus question. It hits the ground when the position or the height is 0. So that makes you plug in a 0 for the height, and now you are solving this quadratic equation. In order to solve a quadratic equation, I think you need the quadratic formula. I like the quadratic formula. I'm a big fan of the quadratic formula. I'll help you with it. T is negative b plus or minus the square root of that b squared minus 4 times the a, which is negative 16, times the c, which is 88, all over the square root of 2 times a, which is negative 32, 2 times 16, negative 16. All right, I want to work through this quadratic formula. I'm going to pick up a calculator here. Give me just a second. Hang in there, or you could help me. I'd appreciate your help. I'm going to work inside there. 56 squared minus 4 times negative 16 times 88. That's a big old number, 8,768. And then I'm going to take the square root of that number. It's not going to be a perfect square. I'm going to round this decimal out. If I get 93.6375, blah, 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 I'm going to actually subtract that from the negative 56. So negative 56 minus that number. And then I'm going to divide by a negative 32. And this is the answer I want, 4.676 seconds. Maybe I round that and call it 4.68 seconds. Actually, I rounded it there to 3 decimals. Here it is to 2 decimals. But that's how long it takes to hit the ground. It's just the solution to the quadratic formula. You know, the quadratic formula has 2 solutions. The other solution would have been a negative number, and that's not the one I want. That would have been this other x-intercept here. But this is what we just found. We found the right answer. And depending on what rounding directions you have, that might be the answer, 4.68 seconds. Cool. Again, that was a little pre-calculus. Here comes, I got a few more questions for you, so bear with me. I'm going to erase these ideas. By the way, what would happen if you took the second derivative of that velocity equation? Remember, the second derivative is the acceleration. What is the second derivative here? What would be this guy's derivative? Can you take his derivative? It's negative 32. And what's negative 32? The acceleration. And what is that? That's the gravity. That's the acceleration due to gravity. So we don't need that, but I just wanted to confirm that while I was erasing. Okay, so here's a few more questions. Here's D. What is the velocity when it hits the ground? And some people make a joke and say, oh, when it hits the ground, it's just laying there on the ground, the velocity is 0. That's not what I mean. I mean, at the moment it hits the ground, it's traveling pretty fast. I threw this baseball up, it's on its way down, and at the moment it hits the ground, right before it hit the ground, right at the moment it hits the ground, what's its speed? What's its velocity? And do I have a velocity formula? Yes, I do. That's this. That's the derivative of the position formula. And so all I need is a time. If I can find a time to plug in, I can get the velocity at any particular time. Well, the previous question said, when does it hit the ground? This is the time it takes to hit the ground. If I want the velocity when it hits the ground, I need this time. So this is pretty easy. I want the velocity at 4.68 seconds. So it's negative 32 times the 4.68 plus the 56. It's this formula with the 4.68 plugged in. Easy, and you should try that. Here comes another question. When does it reach max height? Sorry for my writing. When does it reach maximum height? So that's a good question. By the way, the next question, F, is what is the maximum height? Now the truth is, we do some of these problems in a college algebra class, but what you didn't know, you just kind of got some formulas. What you're trying to do back in a college algebra class is just get the vertex of the parabola. The vertex of the parabola is maximum height. But in calculus, with a little physics and calculus, you know, it reaches maximum height at the moment where it stops for just a second. You know, when I threw this thing, the gravity was slowing it down, slowing it down, slowing it down. It reached its peak, and for just a split second, it stops, and then it accelerates back toward Earth. And so right at that moment, when it reaches maximum height, this is a physics concept, the velocity is 0. Oh, by the way, what's the slope of the tangent line? 0. So the slope is 0, the velocity is 0, the derivative is 0, the velocity is 0, so it reaches maximum height when the velocity is 0. So let's figure out when that is. When negative 32t plus 56, that's my velocity equation, when does it equal 0? I think I'll move the 32t over, set it equal to the 56, divide by 32, so the answer is 56 over 32. I'm going to pick up my calculator, and I'm going to try that. 56 divided by 32, that's 1.75 seconds. That's when it reaches maximum height. By the way, let's just do this one. Negative 32 times that 4.68 plus 56. That was a negative. Velocity can be negative. This was negative 93.76 feet per second. That's the velocity, feet per second. That's when it hit the ground. It was traveling very fast, and it was traveling in a downwards direction, so it was negative. Okay, back to this. We hit maximum height at 1.75 seconds. We hit the ground at 4.68 seconds here. All right, our picture's coming together. All these ideas are coming together. Here's one. What is the maximum height? Well, again, I don't really need calculus. To get the height, when the question asks me for the height, I'm looking for the position, and I wish I had a time. Oh, I do have a time. 1.75 seconds is the time it takes to get to maximum height. So now if I want to know what is the maximum height, I plug 1.75 into the function and do this work. I'll just do that quickly. Negative 16 times the 1.75, squared, plus the 56 times the 1.75, plus the original 88, and I'm getting 137 feet. I hope that's right. I plugged 1.75 into the position equation to get the height. All right, I got one more question for you maybe. So hang in there, one more question. I want to know this. What is the average velocity for the whole trip? For the entire trip is what I'm calling. So, first of all, I'm asking for an average velocity. What did I ask for here? I asked for a height. I asked for when did it reach maximum height. That's when the velocity was 0. I asked for a velocity here, but that was an instantaneous velocity at the moment it hit the ground. But this is an average velocity, and that's not calculus. Remember, that's pre-calculus. I really kind of need two distances and two times. And I'm asking for the entire trip. So let's see here. At the beginning of this trip, I'm trying to do the change in S over the change in time. So what was the original height? 88 feet? And what was the ending height for the entire trip? It was sitting on the ground. The ending height was 0. So I know it went up and down, I know that, but that was its starting height, that was its ending height. What was the starting time? The starting time was 0. And what was the ending time? 4.68 seconds. So that was my change in distance and change in time. And the answer is going to be an 88 over a negative 4.68. So apparently the average velocity is going to come out negative. In other words, it was a little bit of positive velocity there until it hit 0, and then it became negative. Overall, the average velocity is negative, and it is 88 divided by 4.68, and that's 18.8. Negative 18.8 feet per second. Average velocity for the whole trip. I mean, we had tons of little different velocities during that moment, during that trip. We started out with a velocity of positive 56. We ended up with a velocity of negative 93.76. You know, I wonder if you just average those two. I think that might be the answer. If you average the starting velocity with the ending velocity, I think that's a different way to get that answer. That only happens when you have a constant acceleration. Did we have a constant acceleration? Yeah, that was gravity. Our gravity remained constant the whole time. All right, that was fun, you guys. That was a long video, but that was a lot of good stuff. I like that question. And it's not that hard. I think students kind of tend to get a little scared of this physics. But boy, if you read these questions and understand a few concepts, I don't think it's too difficult. I think you can do well. All right, thank you for listening. Do some homework.